So we've some kind of an idea of what the Runge-Kutta does, and let's kind of summarize all this. So you got an initial value problem. Okay, the two-term Taylor method is the Euler method. Same thing, uses lines to approximate uh, solutions of the differential equation. If the solution of the initial value problem is a line, the error in the Euler method, two-term Taylor method, error is zero. Now this is kind of obvious by what the Euler method does, because it goes along the tangent, but alternatively you can say that the error in the Euler method is order of the second derivative, and the second derivative of a line is zero, and so the error in Euler's method is less than zero, in other words, zero. So the global error for Euler's method is order h, and so Euler's method, aka the two-term Taylor method, is said to be first order because the error is h to the 1. The three-term Taylor method uses tangent parabolas, degree 2 polynomials, to approximate. Okay, if the solution of the initial value problem is a parabola, the error in the three-term Taylor method is zero. The third derivative of a parabola is zero, and the error in Hein's method is order of the third derivative. In other words, the error in Hein's method is less than a multiple of the third derivative, and if the third derivative is zero, then in other words, if the solution is the parabola, the error in the three-term Taylor method is zero. The global error for the three-term Taylor method is order h squared, and so the three-term Taylor method is said to be a second order method because the error is order h squared. If the initial value problem derivative is dependent on y, then the three-term Taylor method requires implicit differentiation, and you must understand that that is a pain for you. Okay, with further implicit differentiation, you have the n plus 1 term Taylor method. So you have the 4-term Taylor method, the 5-term Taylor method, etc., which uses degree n polynomials to approximate. So the 4-term Taylor method uses cubics. If the solution to the initial value problem is a degree n polynomial, the error will be zero. The global error for the n plus 1 term Taylor method is order h to the n, and so this thing is said to be an nth order method. Okay, the Euler method then is the first order Runge-Kutta. So what we want for a second order Runge-Kutta method is that, like the three-term Taylor method, is zero error in the solution is parabola. Like the three-term Taylor method, the global error want to be order h squared. It does this by taking a weighted slope, a weighted average of two slopes. Two schemes are presented in the notes: Hein's method and the midpoint method. And then you can generalize that for what you want for the fourth order Runge-Kutta. It is zero error when the solution is a degree 4 polynomial, and that the global error is order h to the 4. The fourth order Runge-Kutta uses four slopes, etc. Okay, so that's your summary of the theory. Is there any more up here? No, there isn't. Now we're just going to discuss briefly the VBA, and actually the VBA is very easy because you kind of just write it down the way it's written. You calculate k's, k, first k, the second k, the third k, the fourth k, and you write this. So you'll calculate. Now you have to be a little bit careful with the x's, and I think you probably put the x's down last. Yeah, you'd probably do that last. So let's hear what it says. So we've been implementing methods by hand on a worksheet. The Runge-Kutta methods you're not going to be doing them by hand, ever. It's even possible doing a worksheet, but really you're talking about VBA. Due to the way we code these methods, using a function will no longer allow the user to specify parameters. Now you can do that if you want, like in the future, or you can imagine doing it, but I won't kind of look at that. It's possible it complicates the code because the derivative will have to be a function of x and y, but also all the parameters, which, as I said, complicates the code because the big F of x, y here is really important. So take an example here. We only want y of x. Okay. So if you're doing this, you only really want y and x. So any of the predictors which you won't see in the code and the ki. You won't be doing that. So what you do first is you define the big f of xy. So that's done there. Yeah. So the parameters make things messy. Now it depends on what method. So we're going to look at step size of 0.5. Okay, so Heinz method. So if your x and your y, and you've got 4 variables x, y, k1, k2. Okay. Step size, okay, initial values, and then let's see what you do. Now it's important that the x is done after the k's, but you do the k. Now look at these formulas. We'll see these formulas in a moment. So this is f of xy, and this is f of x plus h, y plus k1 times h. That's basically these formulas. Look, the k1 is f of xy, and the k2 is f of xi plus h, y plus k1 times h. Now there's a thing about the dependence. If the derivative is independent of y, so there's no y in the derivative, then can use just the first bit. So you wouldn't need f of xy, or you wouldn't need f of x plus h, y plus h. I think there's a similar story for if the derivative, why am I using this stupid color? If the derivative just depends on y, I have to be a bit careful here. I won't say that, but it's possible that you don't need it. Yeah. Okay. Yeah, it actually, if the derivative just depends on x, it's actually, is it complicated at all? It's actually easier, but we'll just assume it isn't. Okay, there is something a bit easier about it when the derivative just depends on x, but I won't get into it. I'll let you kind of discover it yourself. So sometimes the code gets a bit easier. So you calculate the k's, then you calculate the x, and then finally use the last bit of y. So you'll see very, very similar things. So third order, you've k1, k2, k3. You calculate k1, k2, k3, then you do next x, then you do next y. And as I said, with the formula in front of you, when I say the formula, I mean these kind of things. So if this formulas are in front of you, this is not difficult. It might seem very complicated at the moment, but it isn't. Now, I think we're going to look at an applied example. Yeah. So this is it's a damped harmonic oscillator where the spring does not satisfy Hooke's law. So the spring force, you got the normal spring force, but this extra bit here, which is, I think this is a hard spring. And then the epsilon can be negative for a soft spring. And it's saying if x is big, x of t cubed is very, very big. And so it's kind of saying something different will happen when the displacement is very, very big. Yeah, I think if it's a hard spring, what happens is when you stretch it quite far, it's not like you double the extension and the spring force gets twice as strong. It can be like whatever, 8 times as strong. That's a hard spring. And then a soft spring, as you stretch it, it actually starts going plastic. That would be the negative epsilon. I don't know, is that written on the next page? Yeah, the soft spring, stretchy spring. I don't know where I'm going with stretchy, plastic. Grown-ups. Okay. Look at a particular example, and we'll look at Runge-Kutta tree with a step size of 0.01. Now what we have to do is we have to rewrite this differential equation in terms of 2 first orders. So we'll go back and forth and try and figure this out. So up the top, let v be the first derivative, and then differentiate both sides with respect to t. So derivative v is dv dt, and the derivative of the first derivative dx dt is the second derivative. Okay, so we get an equation for x, dx dt is equal to v, and we will want an initial value of x with that. and then we'll go back. So I have the 0.29 cos. This is for dv dt. Oh, by the way, there's in this equation, I've got this. This is an external force. Okay, 1.2t. I need to take away. Sorry, take away so the 0.3 dx dt. So the 0.3 dx dt is 0.3 v. Take that away from both sides. And there was an x and there was an x cubed. And the initial values, I could probably get them off the picture here. So the initial x looks like 1 and the initial velocity was 0. So you can go off and do your Runge-Kutta and this is what you get. You can look at your phase diagram. So the system eventually begins to oscillate in a fashion close to the force damping. Yeah, the external damper eventually will take over. I'm not sure about resonance with this problem. This Duffing equation certainly isn't something where you can solve the problem exactly. Okay. The other example we can look like is interesting one is Fedex Baumgartner jumping out of the plane. Now the interesting thing about it is, so if we write it down, it's not complicated. Mass times acceleration is gravity. So here I think we're taking h to be positive. So if it's quadratic drag, so you got mass times acceleration, okay, the gravity is going down, so it's minus mg, and then it's proportional to velocity, and it's in the up direction, the drag will go up, so it's a plus. Surely it's as simple as that. No, the problem is there's a few problems. G is actually not a constant, and C is not a constant. G actually does vary, like the further you go above Earth, the acceleration due to gravity decreases. And, well, be careful with that. It changes anyway in any case. And C is also a function of altitude because it has to take into account varying air density. So what actually ends up is you end up with these different formulas for the thing. So you can investigate the problem. I think there's a note there if you want to find out a bit more. So this is what G does. G, the acceleration due to gravity, is a function of height. So you can see as the height gets very, very big, it seems to be, yeah, I won't get into that too much. I think if height is, that's possibly height from the center of the Earth. I'm not sure. I won't go into too much. If you look at the air density, you get something like this. Okay, whatever. Now I came up with this approximation to this, which is fine. And you end up with this system. Okay, now the one thing we might just focus on for half a second is this. So the dh dt is v. And if you divide both sides by m, so this is the g, this is, well, there's a bit like, where is it? The formula is a bit complicated. So this is the air density. Like there's a few things going into this formula which I haven't actually mentioned, but this does involve the division by m. But what I'm interested in is the following. We're saying v is equal to dh dt. We differentiate both sides with respect to t. dv dt is equal to the second derivative of height. So this thing here is dv dt, and so we get the equation below, the minus g, which is since turned into positive. We won't worry about that too much. And there's an extra square coming. I don't know what's going on here. Look, maybe this should be plus and this should be minus. In fact, this definitely should be plus and this definitely should be minus. Or have I chosen downwards to be v and upwards to be positive h? Maybe that's what I've done. If I did this properly, Yes, I have chosen downwards v to be positive. So that's where the sign change comes from. That's okay. The squaring shouldn't be there. And you solve them, you end up, now I did this with Runge-Kutta 4, and you end up with something like this. So although the model is rough, we still see some interesting dynamics. As expected, Felix's velocity initially grows linearly. So this is kind of what you'd expect to see. And you expect them to reach some kind of terminal velocity. And that's what you kind of get to see, a kind of a terminal maximum velocity. But what happens then is that as you come into the denser air, the air resistance increases, so the drag increases, and so the velocity decreases to a more conventional terminal velocity. And the big takeaway is it gets a larger velocity in the low density air. Now I wonder what's interesting. Is there any mention of the speed that was reached 1430? I actually, now that looks kind of close. Look, I don't want to lie to you. I don't know if I kind of no, I don't have to lie, because it's 50. So there's no relation there. It's just because it's like 14,000. Yeah. So that's Runge-Kutta, and it's state of the art. So if say, for example, Felix Baumgartner, if he was to analyze what was going to happen, you've got obviously the modeling of the acceleration due to gravity. You've got the modeling of the air density, but when they're actually solving the equations or approximating them, they have no hope of solving them exactly. They have to use numerical methods, and they would try Runge-Kutta.